All right, let's go ahead and finish off this section. Okay, so this example here, we're still doing the same thing, finding the complex zeros. So the first two, they were easily factorable or solvable if I set them to 0. This one here, you're still trying to do the same thing. If you can factor it, great. If not, then you're kind of forced to use synthetic division. Well, this one, that groups. So we can factor it by grouping. Pull off an x squared and then pull off a 25. And then you can pull out the x plus 3. And now you can get your zeros. So -3, and then plus or minus 5i. All right, so moving on to example D. Now this one can't do anything like what we just did in example C or A or B. This one we're just kind of forced to use that rational roots theorem because we can find all the real zeros and then we can get the complex ones kind of at the end. Okay, so let's go ahead and run through it. So 1, -7, 14, -38, and -60. And let's just, I want to pick -1, just because. Okay, so drop the 1, -1, -8, 8, -22, so that'd be -60, +60, so that gives you a 0. Okay, so it was an x to the 4th, this is now an x to the 3rd, so let's use synthetic division again to get it down to an x squared, and then I can go from there. Okay, so let's choose something other than -1. Like you could try it again and see if it works, and if it does, great, but let's just try 6. Okay, so drop the 1, so that would be a 6, -2, -12, 10, 60. So I got a 0, so it worked. All right, so it was x to the 4th. I used synthetic division twice, so that means the degree is now x squared, or a 2. So x squared minus 2x plus 10. Now I have had many a pre-calculus student and calculus students that when they get here, they just go, oh, that doesn't factor, psh, can't do anything else. Well, don't forget, quadratics have more than one way that you could find a 0 or solve them. So just because a quadratic doesn't factor doesn't mean that, well, you're done. Nope, that just means you get to use a quadratic formula or complete the square, whichever one you want to do. So if I use the formula, 2 plus or minus the square root of the -2 squared to give you a 4, minus 4 times 1 times 10, all over 2 times 1, or 2. So inside your square root is now a -36. And that's going to turn into a 6i. And if the radical simplifies like this, then you can see if the fraction simplifies, and it does. So is there a number that goes into 2, 6, and 2? Yeah, 2. So take a 2 out from everything, and you're left with 1 plus or minus 3i. So you have now found all of your zeros. The -1 and the 6, were the real zeros, and then the 1 plus or minus 3i were the imaginary, and so all together those are all of your complex zeros. Okay, so that's how you would do those. So this last question here, where did this concept of imaginaries come from? Imaginary numbers come from? I'm going to link or put a video in this playlist for chapter 4. So it would be the next video in the list. I thought it was a pretty good video that described where these imaginary numbers just sort of came from, and kind of the concept that's sort of driving what an imaginary number is. So you can check that out if you want to. It's not too long, and I thought it was pretty good. It's not too technical, so you don't have to have a master's in math to understand it. Has a neat little visual aid, so check it out.